For decades, Mars has been presented as a world frozen in time, a dead planet, a relic of what might have been. The story told to generations of students and scientists alike was simple and complete. Mars lost its magnetic field billions of years ago. Its atmosphere bled away into space. Water vanished or froze deep underground. Volcanoes went silent. The planet cooled. Life, if it ever existed, died out long before humans looked up at that rust-colored dot in the night sky. That story felt safe. It felt finished. Mars became a geological museum, a place where the drama had already played out, and only the artifacts remained. Rovers were sent to read the epitaph of a world that had been geologically dead for over 3 billion years. The assumption was that nothing truly new could happen there. No eruptions, no flowing water, no chemistry that could not be explained by ancient processes. But something has gone wrong with that story. Not all at once, not with a single dramatic revelation. Instead, the certainty has crumbled slowly, one strange observation at a time. Scientists who built their careers on the dead Mars model now find themselves looking at data that does not fit. Equipment designed to confirm what was already known keeps finding what should not be there. The question is no longer what happened to Mars billions of years ago. The question is what is still happening now. It began with the volcanoes, or rather, with what the volcanoes were supposed to be. Olympus Mons rises higher than any mountain in the solar system, a shield volcano so massive it would cover most of Arizona. For years, it stood as a monument to a violent past. The assumption was clear. These giants erupted when Mars was young and hot, then went silent as the planet's interior cooled and solidified. The lava flows were dated. The craters on top of old flows were counted. Everything pointed to extinction millions or even billions of years ago. Then the models stopped working. Age. Estimates for certain lava flows kept coming back younger than they should have been, not by a little. Some flows appeared to be only a few million years old. In geological terms, that is yesterday. Other features looked even younger. Fresh lava textures, minimal weathering, crater counts that suggested eruptions within the last 100,000 years or less. At first, these findings were dismissed as errors in dating methods. Mars is difficult to study. The surface has been bombarded and weathered in ways that complicate analysis. But the evidence kept accumulating. Different methods, different locations, the same disturbing conclusion. Martian volcanoes may not be dead. They may only be sleeping. What makes this deeply unsettling is what it implies about the planet's interior. A geologically active world requires heat. It requires movement, convection currents in the mantle, pockets of molten rock rising toward the surface. For Mars to have recent volcanism, it must still have a warm and dynamic interior, something the old models insisted was impossible for a planet that size. If the interior is still active, then everything built on the assumption of a cold, dead core begins to collapse. Magnetic field models, atmospheric loss timelines, water history, all of it was constructed on the foundation of a Mars that shut down billions of years ago. That foundation is no longer solid. The ice only deepens the mystery. Mars is known to have water ice at its poles and buried beneath the surface at various latitudes. This was expected. Frozen water on a frozen world, but the ice has started behaving in ways that ice should not behave. Observations of the polar ice caps show changes that occur too quickly. Layers appear and disappear between seasons. The southern ice cap has features that look like active geysers, plumes of carbon dioxide and possibly water vapor erupting through the ice during spring. These are not fossil features, they are happening now. Every Martian year, the surface transforms. Dark fan-shaped deposits spread across the ice. Something is moving beneath the frozen surface. Subsurface ice presents an even stranger problem. Ground-penetrating radar has mapped vast sheets of ice buried under dust and rock, sometimes just a few meters below the surface. In some regions, this ice appears to be far purer than it should be. On a planet where dust storms rage and material mixes constantly, pure ice requires an explanation. It suggests the ice formed recently or is being replenished by some process not yet understood. Then there are the slopes. Certain crater walls and canyon sides show what look like water-carved gullies. Fresh gullies. Some appear to have formed within the last few decades. Dark streaks flow down slopes during warm seasons and fade during cold ones. For years, scientists argued over whether these features involved liquid water or just dry flows of sand and dust. The debate has not been resolved, but it has shifted. Evidence now suggests that at least some of these features involve briny water, salt-laden liquid that can remain unfrozen at temperatures well below 0 degrees Celsius. If true, it means liquid water still flows on Mars, however briefly, however rarely. A dead planet does not have liquid water on its surface, but water and ice are only part of the equation. The atmosphere itself has become a source of profound confusion. Mars has a thin atmosphere, mostly carbon dioxide, with trace amounts of nitrogen, argon, and other gases. It should be simple, stable, predictable. It is not. Methane keeps appearing where it should not exist. Methane is a fragile molecule. Ultraviolet radiation from the sun breaks it apart in just a few hundred years. For methane to persist in the Martian atmosphere, something must be producing it. On Earth, methane comes from two main sources: geological activity like volcanic vents, or biological activity like microbes. On Mars, neither was supposed to be happening. Yet methane has been detected. Not constantly. That would almost be easier to explain. Instead, it appears in plumes, concentrated bursts that show up in one region, then vanish. The levels fluctuate with the seasons. Some measurements show spikes 40 times higher than background levels. Then the methane disappears, as if it was never there. This should not be possible. If methane is being produced, where is it coming from? If it is being destroyed, what is breaking it down so quickly? Some researchers have proposed that methane is being released from ancient reservoirs trapped underground, liberated by cracks opening in the rock. Others suggest chemical reactions between water and rock could generate small amounts. A few have quietly pointed out that microbial life would also fit the pattern. No explanation feels adequate. The methane appears and vanishes according to a rhythm that no one can predict or fully explain. It suggests Mars has an active chemistry that operates on timescales faster than expected. The planet is exhaling something into its atmosphere, and then that something is erased before it can accumulate. The organic molecules make the situation worse. Organic molecules are carbon-based compounds, the building blocks of life, though they can also form through non-biological processes. For years, missions to Mars searched for organics and found almost nothing. The surface seemed scrubbed clean, sterilized by radiation and oxidizing chemicals in the soil. Then rovers began drilling. A few centimeters below the surface, protected from radiation, organic molecules were found. Not just traces, complex chains, thiophenies, benzene, compounds that on Earth are associated with ancient life or geological processes involving heat and pressure. The molecules were found in rocks that formed in ancient lake beds, places where water once pooled for thousands or millions of years. This was expected to some degree. Ancient organics in ancient rocks. But then organics were found in younger rocks, in places where the chemistry should have destroyed them, in concentrations that seemed too high for random geological processes, and the types of molecules kept expanding. Each new sample brought compounds that required explanation. The most disturbing aspect is not just that organics exist. it is that their distribution makes no sense under the old models. If Mars has been a sterile, radiation-blasted desert for billions of years, organic molecules should be rare and degraded. Instead, they appear to be widespread and, in some cases, surprisingly intact. Either the surface environment is not as hostile as believed, or these molecules are being protected or replenished by processes that remain invisible. Seasonal changes add another layer of strangeness. Mars has seasons because its axis is tilted, much like Earth. As the planet orbits the Sun, different hemispheres receive more or less sunlight. This should cause predictable changes. Ice advances and retreats. Dust storms form. Temperatures rise and fall. But the changes observed are not entirely predictable. Dust storms that should be regional sometimes engulf the entire planet with no clear trigger. The timing and intensity vary in ways that suggest the atmosphere is more dynamic than models predicted. Surface features change between seasons in patterns that imply active processes, not just passive weathering. The polar regions show layered deposits that record climate variations over millions of years, much like ice cores on Earth. But the layers contain surprises. Periods of heavy dust deposition alternate with periods of ice accumulation in cycles that do not match orbital models perfectly. Something about Mars's climate system is more complex than the simple equations suggested. Recent observations have documented changes in the brightness of certain surface regions over just a few years. Patches of ground darken or lighten. In some cases, this can be explained by dust being blown around. In others, no clear explanation exists. The surface is not static. It shifts and changes on timescales short enough for human missions to witness directly. All of this points to a single uncomfortable conclusion. Mars is not the dead world it was believed to be. It remains active in ways that are subtle but undeniable. The planet still has internal heat. It still has chemistry happening at its surface and in its subsurface. Its atmosphere is not in equilibrium. Its ice is not simply frozen in place. Somewhere beneath the dust and rock, processes are unfolding that the old models did not account for. This raises the most difficult question. If Mars is still active, what does that mean for life? The search for life on Mars has always been framed around the past. Scientists looked for evidence that Mars once had the right conditions: liquid water, organic molecules, energy sources. The assumption was that if life ever existed, it died out billions of years ago when the planet lost its magnetic field and its atmosphere thinned. The best hope was to find fossils or chemical signatures locked in ancient rocks. But if Mars is still geologically and chemically active, that assumption collapses. Active geology means heat. Heat means energy. Energy means the possibility of life, not in the past, but now. Deep beneath the surface, where ice melts into liquid water and minerals react with that water, there could be environments similar to the deep subsurface of Earth, where microbial life thrives kilometers below ground, cut off from sunlight, feeding on chemical reactions in the rock. The methane plumes could be biological. The organic molecules could be fresh, not ancient. The seasonal changes could involve microbial populations expanding and contracting with the availability of water. None of this is proven, but none of it can be ruled out anymore. What makes this possibility so unsettling is how long it was ignored. For decades, Mars was studied as a fossil. Missions were designed to look backward, not to detect active processes. Instruments were built to analyze ancient chemistry, not to monitor living systems. If life exists on Mars today, it has been hiding in plain sight, in the data that did not fit, in the anomalies that were dismissed as noise. The realization that Mars may still be alive in some sense forces a rethinking of planetary science itself. For years, planets have been categorized as active or dead based on size and age. Earth is active because it is large and retains heat. Mars is dead because it is small and cooled quickly. This binary thinking now seems inadequate. Activity exists on a spectrum. A planet does not have to have plate tectonics and a global magnetic field to be dynamic. It can simmer. It can have localized pockets of heat and chemistry. It can surprise? What went wrong with the old models? Part of the problem was data. Early missions to Mars provided snapshots, not continuous monitoring. A few images, a handful of measurements. Scientists built models based on incomplete information and then defended those models as new data came in. Anomalies were explained away. Uncomfortable findings were attributed to instrument error or misinterpretation. Another part of the problem was assumption. Mars was expected to follow the same rules as Earth, just scaled down and switched off. When it did not, the tendency was to adjust the interpretation rather than question the framework. The idea of a geologically dead Mars became so entrenched that evidence to the contrary was met with skepticism, even resistance. But the biggest problem may have been hubris. The belief that a planet could be fully understood from a distance, that a few decades of observation could capture billions of years of history, that the story was simple and complete. Mars has shown that planetary science is still in its infancy. Every answer leads to new questions. Every certainty eventually cracks. The implications extend beyond Mars. If a planet that was confidently declared dead turns out to be active, what does that mean for other worlds? For the icy moons of Jupiter and Saturn, where subsurface oceans are suspected? For the countless exoplanets being discovered around other stars? The criteria for habitability may need to be rewritten. Worlds once dismissed as too cold, too small, or too old may harbor hidden activity. Mars is teaching a lesson in humility. The red planet, so familiar and so studied, is still largely unknown. Its interior is a mystery. Its chemistry is strange. Its history is incomplete. Decades of missions have revealed more about what is not understood than what is, and the exploration is far from over. Future missions are planned to drill deeper, to search for biosignatures, to monitor the atmosphere and surface in real time. Each new data set will likely bring more surprises, more contradictions, more evidence that the simple story was wrong. There is something almost disturbing about the way Mars keeps defying expectations. It is as if the planet is withholding secrets, revealing them only slowly, only when observers are ready to admit ignorance. The methane that appears and vanishes, the ice that moves, the organics that should not be there. These are not just scientific puzzles. They are signals that the universe is more complex and strange than models allow. Mars was supposed to be the easy case, a nearby planet, similar to Earth in many ways, observable with telescopes and rovers. If understanding Mars has proven this difficult, what hope is there for truly alien worlds? Perhaps the most unsettling realization is this: Mars may never be fully understood, not because the tools are lacking or the data insufficient, but because planets are not static objects with fixed properties. They are systems, dynamic, evolving, interconnected systems that change over time in ways that cannot be fully predicted. Every snapshot is just that, a moment in a process that stretches across billions of years. The dead Mars was comforting. It was a cautionary tale about planetary death, a reminder of what Earth could become if its magnetic field failed or its oceans evaporated. It was a place where the drama had ended and only the ruins remained. The living Mars is far more troubling. It suggests that planetary processes do not simply stop, that even small cold worlds can harbor hidden fires, that the line between dead and alive is blurred and uncertain. It raises the possibility that life, once started, is harder to extinguish than anyone imagined, that it finds ways to survive in cracks and shadows, in frozen ground, and toxic air. Mars is not finished. The volcanoes may erupt again. The methane will continue to appear and disappear. The ice will shift and crack. The organic molecules will accumulate in sediments, waiting to be discovered. And with each new finding, the certainty of the past will erode a little more. Scientists will continue to study Mars, to build new models, to propose new explanations. Some will cling to the old story, adjusting it at the edges to accommodate inconvenient data. Others will embrace the uncertainty, accepting that Mars is stranger and more active than once believed. But the truth is already clear. Decades of assumptions were built on incomplete evidence and wishful thinking. The story told about Mars was not the whole story. It may not even have been the right story. What was presented as fact was often speculation. What was declared certain was merely probable. Mars was never fully understood. It was never truly dead. And it is not finished, surprising those who thought they knew it. The red planet remains a mystery, waiting beneath its dust and ice, exhaling methane into a thin sky, hiding organics in ancient rocks, moving water through frozen ground. A world that refuses to fit into the categories assigned to it. The old certainty is gone. What replaces it is not another neat story, but a recognition of complexity, an admission of ignorance, a quiet, unsettling awareness that the universe does not conform to expectation, and that even the most familiar worlds can turn out to be strangers. Mars is still here, still active, still changing, and everything believed about it may have been wrong.